This is atoms and periodicity and spectroscopy homework number 1. Let's look at number 11. If you're here just to check your answer, the answer to number 11 is 65.40 AMU. So that's the answer. If you got it, you can move on. If you didn't, let's look at how to solve it. Well, the way we solve these is we do the calculation based on the number of isotopes. So there's 1, 2, 3, 4, 5 isotopes. That means we're going to need 5 parentheses. So I'm going to start way over here, and we still may have to do 2 lines. So let's see. This first one right here, the mass is 63.929, and it is times its percent abundance. Let's see, it's 64, so it must be this one. So I'm not going to do 48, I'm going to do 0.4863. Then I'm going to add it to, and we're going to keep doing that. So there's going to be 5 parentheses, 1 for each isotope. So this is what the work would look like, going through one at a time. Now, if you didn't get 65.40 AMU as your answer, I'm noticing this worksheet might actually have a mistake in it. Do you see how this one and that one, boy, the peak heights look really different. This one looks much bigger than that one, but they say that the abundance is the same. Either the graph is wrong or they have a typo up here in the problem somewhere. And I noticed on the answer key, they say that this one really is 4.1%, but that this one is not. They say that this one is 0.00. Oh, wait a minute, got it backwards. This one is 0.00620, as in it's 1, 2, it's 0.6%. So that might explain it if you got the wrong answer. It may mean that you know what you're doing, but that they just had a typo in here. So obviously I'd accept either answer, either this one or the one if you calculated out the way, if you calculated the way it was originally. If you're looking for places to make mistakes, you remember that 4% is not 0.4, it's 0.04, and 0.6% is not, it's 0.006. So those are the things that I think people are likely to miss. Number 13 wants us to calculate the mass percent of each element. So the mass percent of carbon would be essentially the mass of all the carbons divided by the total mass of the compound. Well, if you add up the total mass of the compound, you get 100.09 AMU. So that's the mass of calcium carbonate. That's right, CaCO3. And on top we have to have the mass of the carbons. And you notice there's only one carbon in there, so it's just going to be 1 times 12.01. And then all we got to do is take all of that times 100. And our percent for carbon turns out to be 12%. And if we do the same thing for calcium, let's do it in a different color. It's not going to do that. Anyway, let's do it in a different color. So calcium, it would be the same total mass on bottom, but on top, let's see, we got 1 calcium as well, so the mass of calcium is 40.08 AMU times 100. And our answer turns out to be 40.04%. And then our percent of oxygen is a little bit different because, yes, we do the same mass on bottom, but on top we're going to do 3 times our mass of oxygen, which is 16.00 AMU. So there's the important part, because we have 3 oxygens, times 100, and our percent of oxygen turns out to be 47.96%. And it's always a good idea to check this, that, and that should all add up to be 100%. Let's see, 87, 96, that's pretty close. And since they're measured numbers, it may be a little bit off, but that's pretty close. Let's look at number 14. So you have two separate pure samples of carbon dioxide and they're analyzed. Both samples are found to contain 17.29% carbon by mass. You know, this question didn't ask it, but it's a good one to think about. How could you figure out if this is the percent carbon by mass, how could you figure out the percent oxygen? And you remember that the whole thing has to add up to 100, so if you did 100 minus 17%, you could figure out the percent oxygen. But that's not what they're asking you. They're asking you why essentially all samples of CO2 have the same percent carbon and percent oxygen. Now this is one of these no-duh moments where it seems really obvious, but they're talking about early atomic theory and that wasn't really obvious. So there's two things that we need to consider here. So the first one is the law of definite proportions. Now this one is pretty obvious to most chemists, but not many of them can actually cite what it is. And what it is atoms combine in whole number ratios to make compounds. In other words, you're never going to see CO 1/2. They have to combine in whole number ratios. That's not going to work. And the ratio that they combine in, and you notice we're talking about CO2, it's not CO3. Now you might think, well, I've seen CO3, but that's a polyatomic ion. There's always a specific way that they combine. MgO, it's never Mg2O, and it has to do with charge or other atomic structure. So the ratio will be determined by the atomic structure of each element. There's a lot of different ways to say the law of definite proportions, but essentially what you're citing what you already know. If I know the charges, I'll know the ratio. And they have to be whole number ratios, no fractions in compounds. So that's one reason why all CO2 samples have the same mass percent. So the second thing that really matters here is not part of the law of definite proportions, but it has to do with isotopes. While atoms like carbon have more than one isotope, and therefore you might expect that a CO2 molecule in Russia might have a different ratio of carbon-13 to carbon-14 than it does in the US, turns out that that's not true. The abundance of each isotope never changes from sample to sample anywhere in the world. The percentage of carbon-12 in a carbon sample is always the same, no matter where in the world you get it. That's a pretty profound statement. It seems obvious, but it's a pretty profound statement. And that's why all CO2 molecules have the same mass percent. So I didn't do it. You might want to add one concluding statement saying, therefore, that's why they all have the same mass percent. Now lastly, 16. Now you notice I haven't changed the slide here. And the reason is, in 16 you'll see it's a very similar question. They're talking about a different compound, but they're saying it's 36% iron by mass. What difference would there be if I had a 150 gram sample or a 450 gram sample? And of course, there would be no difference in mass percent iron. The percentage of that sample that's made up of iron would be the same. There would be more iron, but there'd also be more titanium, and there'd be more oxygen. And it's for the same reasons that we cited right here, because the law of definite proportions says that this compound is going to assemble in that ratio, always, everywhere you look in the world. So, if you watch this video, you, for number 16, can simply write C answer to number 14, and you're done, because it's exactly the same idea.